All right, very good. And let me give you a moment to copy down the example here. All right. Okay, so in this problem, we have a crate that's hauled 8 meters up a ramp under a constant force of 200 newtons and applied at an angle of 25 degrees to the ramp. What we want to do is we want to find the work that has been done. Find the work that has been done. So, do you remember the definition of work? How is work defined? That's right. Force times distance. Good. Force times distance. And this is sort of like your, maybe 9th or 10th grade definition. So that's fine. That's fine. So this, if you're pushing an object across the floor with a certain force and the object moves a certain distance, you get your work. Okay, you compute your work. Now, the thing is, in this case, we have a crate that's being hauled up a ramp. Okay, and the force that is being applied to the crate is 200 newtons, but it's at an angle of 25 degrees to the ramp. So it's not like we're pulling the crate. It's not like we're pulling the crate like, horizontally, so to speak. So let me ask you, what would be helpful for us to do this problem? What would be very helpful to have?
A diagram.
A diagram, definitely. Absolutely, everybody. So let's get to a diagram. Okay, so here is my ramp. Here's my ramp. And the crate is here. Okay, I mean, I just have a dot for the crate, but that's my crate right here. And I'm moving it up the ramp. And to pull the crate, I'm applying a force at an angle of 25 degrees to the ramp. So what I've done is in this picture, I've created my force vector. Okay, so you learned about vectors in section 9.2. And then I have a distance vector. Okay, that is basically the ramp. Okay, so I can break the problem down into a force vector and a vector, a distance vector that goes in the direction the object's getting moved. Now work is still force times distance, right? But we have to compute the work relative to this more complex situation. And remember, class, on the right in your viewer, there's a thing for zooming. If you want to like blow up the picture, blow up the document, you can use that zoom feature. So, okay. Now, I'm drawing, hold on here. Okay, here's a red, well, no, hold on, no. When I apply the force to my crate here, hold on. Here's my crate right here. When I apply the force to the crate, is the entire force being used to do the work? If I'm applying the force to hauling the crate at a 25-degree angle to the ramp, is that whole force being utilized in doing the work? No. What's the part of the force that does the work?
The component along the x-axis of the force.
That's right. That's right. And who said that? Was that Ian?
It was me, Hyun.
Oh, who knew? Yes, you're absolutely right. Absolutely right. It's this part, because the object is moving along the ramp. So it's just the component of the force that is parallel to the ramp that's doing the work. Okay, and so, all right. Given that, we'll call that the length of that vector, that red vector, x. So since we do have a right triangle here, the cosine of 25 degrees is equal to adjacent over hypotenuse. So that we would equal x over the magnitude of the force, which is the length of the force vector. So x is equal then to the length of the force vector times the cosine of 25 degrees. Okay. Now work is equal to force times distance. But remember, the component of the force that does the work is equal to the magnitude of the force times the cosine of 25 degrees. All right, and then the distance would be the length of your distance vector, which is the magnitude of the distance vector. So you end up getting then that work is equal to the magnitude of the force vector times the magnitude of the distance vector times the cosine of the angle between them, cosine of 25 degrees. And this we call the dot product. This is so how many recall from their hold on here. One moment. How many recall from their homework that the dot product is equal to the magnitude of A times the magnitude of the B vector? Good, Ian. times the cosine of the angle theta between A and B. So you might wonder, well, where did that come from? Why is that important? Here we go. We need to use the dot product to compute work. And so we know the length of the force vector is 200 newtons. The distance vector is in meters, 8 meters. And the angle between them is 25 degrees. So we get 1,450 Newton meters. And that's how you compute the work. Okay. Are there any questions on that? How many have seen this maybe in a physics class? Okay, Charles and Eli are familiar with it. Okay. And Andrew and Gordon, wonderful, wonderful. Okay, well, are there any questions before we move on? Yes, Mario, I understand. I understand. You'll find actually dot products come up in linear algebra, and linear algebra has many economic applications. And actually, calculus 3 has some economic applications too. I mean, it does. But all right. Well, very good. Well then, very good. If they're very good. If there are no questions, then let's go to the next example. Okay, projection vectors. Okay, so, and I'm gonna let you copy this example down. Okay, so in this problem, we have a vector B and we have a vector A. And we want to find the projection of this vector B, which is equal to 5i. Now, 5i, we could express in this notation as 5, 0. And then, and then the vector 3i minus 4j, we can express as the vector 3, negative 4. Okay. So, what would help us a lot just to do this problem? What would really be helpful?
The dot product.
Yeah, well, the dot product will be useful, Hyunwoo, but also we want a diagram. Let's get a diagram up here, as Ian suggested. And this will also show you, what, for some of you, projections might be new. So, okay, here's a picture. Here's a picture. Okay, I have an XY axis. And I have this vector B right here. okay, which is goes to the point 50. And then I have this vector A. Which goes to the point 3, -4. So if we were to take the vector B and graph a perpendicular down onto vector A, okay, if we were to basically take the vector B and project it onto the vector A in this perpendicular fashion, so to speak, then the projection vector would be this red vector here that I'm drawing. This would be your projection. This is called projecting the vector B onto the projecting the vector B onto the vector A. Okay. And the book actually has some nice diagrams as well in section 9.3. But I thought that what I'm doing here, if you look at like figures 5 and 6, they have nice pictures also. But I think this hopefully gets the idea across of what a projection is. So let me give you a moment to copy the picture down. Okay, and then we'll talk more here because I mean we want to find what that red projection vector is. You know what? Hold on here. You know what? What is this red vector? All right, so I'll give you a moment. Please let me know if you have any questions. Okay, so hold on, sorry. This phone keeps. Okay, good. So how are we going to find this projection vector? Well, look at the triangle that's created by the vector B and the perpendicular drop on to the vector A and then the projection vector. That triangle is a right triangle, right? And that's always going to be the case. Now, there's an angle theta here. And, you know, and we know the dot product is going to get involved in here, right? So the cosine of theta is equal to the length of the projection vector, which is the adjacent side, in that right triangle, there. So the cosine of theta is equal to the length of the adjacent side over the length of the hypotenuse. Well, the hypotenuse would be the vector b. Okay. So the length of the projection vector here would then have to equal the length of the vector b times the cosine of theta. But we know the definition of the dot product is that a dot b equals the length of the vector a times the length of the vector b times the cosine of theta. And so this means then that the length of b times the cosine of theta, well, we can divide this equation by the length of a. And so that means then that the projection, the length of the projection vector of b onto a is equal to a dot b, that dot product, divided by the length of a. And we call this the scalar component. This let me just see here, one moment. Well, it's a number, right? It's a number. So we call that the component. We call that the, I want to be a little careful here how I phrase this. Let me just phrase this here. The book calls the scalar projection of B onto A. That's what they call that. That's COMP. The book denotes that as the scalar projection of the vector B onto A. Okay, and we can get that scalar projection because we just compute the dot product of A and B over the length of that vector A, and we'll get 3. Okay, so let me know if you have any questions so far.
So, Professor, what are the primary uses we have for the scalar projection and the vector projection?
Well, of course, in linear algebra, the projection vector has, you see it a lot in linear algebra in Math 284, where you're trying, for instance, to, if you want to, like how many have heard of like a least squares problem, like a line of best fit through
Yes.
points? Yeah. That line of best fit is actually a projection vector. It's a projection, and in calculus 3, I mean, I know I'm sure there are many. Well, like you can use it, for instance, if you want to find a formula for the distance from a point to a line. Okay. That's actually exercise 41, but there they just give a formula. I mean, you can take this projection idea and derive other concepts in calculus 3. I have seen it used more. Personally, I've seen it used more in linear algebra, but there's an example of multivariable calculus where it's used. Sure, no problem. Now, we get a value of 3. And I ask here, is that reasonable based on the picture? Is it reasonable based on the picture? So if you think about the red, you know, the vector B, is how long? How many units is the vector B? Five units. That's right. That's right. How many units long does the red projection vector look to be? How many units long does that look to be? Well, so I was hoping a bit more than 2, less than 5.
I think we
Could
should be
we be
looking at
more
4.
exact? I'm sorry?
Should we be looking at 4 for this? If we look at our blue vector as the hypotenuse and our red vector as the adjacent.
Yeah, well, the blue vector is the hypotenuse in that right triangle. The blue vector B is the hypotenuse. It has length 5. And I'm wondering that leg, that red vector, which is the leg, that's right, Hunwoo, that has length 3. The projection vector has length 3. If you rotate that vector, like, you know, like think of like rotating it in a circle, you rotate it. Actually, hey, this would be an opportunity to use my, let me see here if I can do that. Maybe I can do this. If you were, well, no, I was hoping I could draw like a curve, you know. But let me see here. Let me just try something, class. How, well, it's not, let me just, all right, hold on, I have to take that off. What I'm trying to say is the length of this projection vector is equal to 3. Okay, the length is equal to 3. And yeah, that's its length. Okay, so maybe the picture's not drawn perfectly here. I think the reason is there's a little bit, maybe too much space here. But the point is the length of it is equal to, the length of it equals 3. Are there any questions on that? All right, so what I'm trying to do is geometrically help you understand what these things mean. So the scalar projection of B onto A is just the length of your projection vector. Now, if you want to find the projection vector, you need direction. What direction is this red projection vector here? What direction is it going in? What direction is the red projection vector going in? It's going in the same direction as the vector A. That's right, Eli. So if we were to consider this 3 as a multiple of a vector going in the direction of A, we could get the projection. And what that would be is this. The vector projection of B onto A is going to be equal to 3 times the vector A divided by the length of A. So it's going to equal 3 unit vectors in the direction of A. If you take the vector A, and divide it by the length of A, you get a unit vector. How many recall that? Maybe from their homework, getting a unit vector. Yeah, Mauro recalls it. Well, that's a unit vector. So if you go 3 steps, 3 unit vectors in the direction of A, you'll get your projection vector. And that then is just going to be equal to 3 times the vector given by 3 negative 4 over the 5. 5 was the length of A. And so that'll get you the vector 9/12 and negative 12/5. Actually, my picture's pretty good. You know, I checked that out. If you look at if you go back to the picture, you'll see that that projection vector does, if you look at like, let me just go back here, 9/5, negative 12/5. I'll go back, don't worry, class. Here, this here, does it have coordinates 9/5, negative 12/5? 9/5 is almost equal to 2. So yeah, the x coordinate here, here's 2. The x coordinate almost looks like pretty close to 2. And then negative 12/5 is a little bit more than negative 2. And yeah, this is the y coordinate's a little more than -2. So that actually is pretty good. And in terms of the length, I think I don't know why the little circle thing wasn't working the way I wanted it to, but the length of that vector, well, you know, you have to draw it perfectly, but it equals 3. So let me go back here to the notes, and it is reasonable based on the picture. And then here, this is if you want a formula for the projection of the vector B onto A, that's the formula we used. And that can be rewritten like this. So, yeah, Hyunwoo, you had a question? Hyunwoo?
Yeah, can you go back one slide?
Yeah, I'll tell you what, I'll go back one slide, but let's let folks copy this down real quick, and then we'll go back one slide for sure. Don't worry about that. Don't worry about that. We'll go back. This is one of the limitations of remote teaching. You know, you have to, if it were like a whiteboard, it would all be there on the whiteboard, and I could just, you know, but all right, before I go back to the slide, are there any questions at all on this? How many are feeling reasonably comfortable with this concept? Good, excellent. And by the way, this can be then for vectors in three-dimensional space. The formulas are the same. Hyunwoo, let me go back to the previous slide. One moment. Okay, there's the previous slide. Yes.
My question is the part where we have projection B onto A, and then
Yes.
under it you have like it like sort of underline bracket or something, and then it says component of B onto A.
Yeah, this is just notation. The scalar projection of B onto A, they denote that with using this notation.
What's the difference between the okay?
Well, this is a number. The scalar is a number. So I personally don't think it's the best notation. What I mean is I don't think it's the best words, so to speak. But what this is this is the length of your projection vector. That's what this is.
Okay, so we're gonna is like what's COMP stand for? Component?
Component.
Okay, and it's like just the component.
The scalar component of the vector B onto A. Think of it like that.
The scalar component of the scalar projection?
That's right. Only the component is like it's one component going in the direction of the vector A.
Okay.
It's like the vector A is like the direction you're going, so to speak.
All right, thank you.
Okay, great. All right, are there any other good questions? Okay, well, let's do one more example. One more example here. Dot product. One more example. Okay, I'll let you copy this down. Okay, so for this problem, well, you know, if we have two lines, okay, and call this line L1, this line L2, for instance. Okay. All right. We want the acute angle between the two lines. Okay. So which is the acute angle? Angle 1 or angle 2?
Angle 2.
Angle 2. Okay, so, all right, we know we're looking for the acute angle. So if we were to end up doing the problem and getting an angle more than 90 degrees, what would we do to find the acute angle? I mean, let's say we worked the problem and we ended up finding this angle here, angle 1. What would we have to do to get the acute angle? Can we find the subtract? Okay. Well,
so from 180 degrees, we'd subtract our answer.
That's right. That's right. Good. And Eli, Gordon, and Andrew agree. Okay. So, do you think what's the key feature of a line? What's the key, very important feature of any line?
Magnitude and direction.
Okay, a line does have magnitude and direction, and Emma's mentioning slope. Do you think slope helps us determine the direction of a line? It absolutely does. It absolutely does. As a matter of fact, it doesn't matter. You know, like if you have like say you have two lines here. Let me erase this picture right for the moment. Let's say you have, well, I guess this thing I gotta, you know, just kind of, I have two lines. Hold on here. Two lines. And I have an X and a Y axis. Do the two lines have the same slope? Those two black lines? Yes, they do, because those lines are parallel, right? Do the two lines have the same y-intercepts? Are the y-intercepts the same? No, they're not. So what determines direction of a line is its slope. So what we need to do is to find the slopes of these two lines. Okay, we have to find the slopes of the two lines. So let's go to the solution here. Line L1 is this line here, x plus 2y equals 7. I'm going to put the line in y equals mx plus b form. So I can determine the slope of the line. Okay. Slope is -0.5. Okay, and so the slope of the line is -1/2, and we know the rise and the run. Let you catch up to here. Okay, now the slope of the first line is -1/2, and so a vector parallel to the first line is 2, -1. I'll call that vector A. So 2 is x. Think of the x component. X is 2, y is -1. So if we were to draw the vector 2, -1. Hold on here. Let's say this is 2. And let's say this is -1. Okay, the vector 2, -1 is this vector, right? That's my vector A. And do you see how the slope of that, if you think about, again, a right triangle, okay, the rise, the run is 2, the rise is -1. That vector would point in the direction of a line that has a slope of -1/2. Is that okay? Are there any questions on that? All right. Well, similarly, for the second line, we determine the slope is 5 or 5/1. So a vector parallel to the second line is going to be 1, 5. Now, please let me know if you have any questions on this. So for our two lines, we have two vectors, vectors A and B, that are parallel to those lines. So the angle between the vectors is going to have to model the angle between the lines, right? the angle between the vectors has to model to be the same as the angle between the two lines. Well, how are we going to find the angle? What are we going to have to use that you learned? What special operation between two vectors? That's right, Eli. I hope I'm pronouncing your name right, Eli. Dot product. I tell you what, Ellie, is it Ellie number one or okay? Thank you. I was thinking it's that. Yeah. Okay. Thank you, Ellie. So okay. So we got to use the dot product. Okay. So we'll go to the next page if that's all right. The lines meet at the same angle, theta, that the vectors meet at. And so we have to find the angle between the vectors. And you know from the homework that you did that the dot product is going to be involved. So the dot product equals -3 in this case. The length of A is square root of 5. The length of B is square root of 26. Okay. And the cosine of theta, by the definition of the dot product, is equal to the dot product of A and B divided by the product of the lengths of A and B, and that equals -3 over root 130. And from there, you can get theta by taking the arc cosine. Let me stop for a moment, let you catch up. Please let me know if you have any questions.
So how did we convert from the y equals mx plus b equation into vector notation?
Well, the key is this statement up here. One moment. Let me get my pen here to circle it. All that matters is what the slopes of the lines are. The lines, you know, because the way the slopes are defined, the slope by definition is rise over run. Well, the rise corresponds to the vertical component of the vector, and the run corresponds to the horizontal component of the vector. So if we know the slope, and you know, if we get an integer like 5, remember one of those lines we had 5 for the slope, we can write 5 as like 5 over 1. That gives us the rise and the run. So that line with the slope 5, 1 would be parallel to the vector that has horizontal component 1 and vertical component 5. So finding the angle between the two lines is equivalent to finding the angle between the two vectors. And that's why we're able to use the dot product.
So once we have both vector x and y's from the two equations, we just resume to these steps, the
That's
one.
correct. That's correct. That's right. And now we determine that theta, we get 105.3 degrees. But that's not the answer, right? That's not the answer because we're looking for the acute angle. So what would the acute angle be between the two lines?
Will we do -1? Actually, I don't know.
That's right. Emma has it. You're on the right path there, Hunyu. Emma and Andrew have it there in the chat line there. Yeah, you're going to take that 105.3 degrees and subtract it from 180 degrees. So this is a very nice problem. Oddly enough, the website I don't think gives a help video with it, but you know, this problem really is one that involves a lot of geometric understanding, and that's why I wanted to do it with you. Well, one reason, of course. Okay, well, so our final answer then is 74.7 degrees. All right. Please let me know if you have any questions. Hyunwoo, you're good?
Yeah.
Or a little more comfortable? Okay. All right. Okay. Well, then let me stop the recording.